Good afternoon, all. So we will start the afternoon session. So here we have the session on smart sensors in IoT. Dr. Joseph is a resource person, and we are very proud to introduce Dr. Joseph, one of our great, one of our proud alumnus, and studied his undergraduate course in LBS College of Engineering, Kasaragod, and later he did his master's in NIT. Then he did his PhD from IIT Hyderabad, and now he's working as an assistant professor at Indian Institute of Information Technology and Management, Kerala, Tiruvandhuram. He was working as a postdoctoral researcher in E.L. Jinsen Laboratory at Stanford University, USA. He also worked as a research associate in Center for Nanoscience and Engineering, and Mechanical Engineering Department in the Institute of Science, Bangalore. In his research career, Dr. Jose focused on developing novel ultrasound transducers for imaging, biometric, and airborne applications. He also worked on developing miniaturized biosensors and sensors for precision agriculture. He has 7 years of microfabrication experience. His primary research interest is applied ultrasonics, that is for neuromodulation, fingerprint detection, airborne navigation, etc. So we extend our warm welcome to Dr. Joseph. Over to you, sir.
Thank you so much, ma'am, for introducing me. It's been a great pleasure to be here to interact with all of you. Rather, it would be more happy if it was in-person interaction, but unfortunately, because of the current situation, we cannot do that. But let's try to make it kind of interactive and kind of more oriented towards day-to-day life applications, so that rather than just hearing a boring talk, let's try to understand whatever topic that I'm delivering today uh, with at least some meaning in your career. So let me stop my video because I think we could have some bandwidth issues, so it would be safe to have it closed. I guess I am audible. So let us start today's discussion on smart sensors in IoT. Um, Whenever you are starting a topic, it's good to start with a question. So my question today is that why are sensors important in IoT? This is a very basic question that anybody could answer. So typically in Kerala, what happens is that, especially towards the southern part of Kerala, when you ask a question, people tend to answer the question with another question. And so I have another question as an answer for this question. So this similar question for that is, why do we need eyes, nose, ears, tongue, and skin in a human body? If you know the answer for these, you know the answer for my question. So how these five organs are important in a human body? Exactly in the same way, sensors are important in IoT. So to give analogy in a better way, let us understand a human body as an internet of thing, right? You can understand in that perspective. If you look at how your eyes, your nose, ears, tongue, and skin work, and how they coordinate your day-to-day activities. For example, when you're walking, your eyes will understand if you have an obstruction in front of you, or if you can walk forward. So eyes will take images, it will convey to your brain, and then your brain will pass the information to your legs, saying that okay, you don't have a way forward, or you have a way forward. So in the same way, sensors are important in IoT because sensors sense the physical phenomena, and it gives an input to the central processing system, and where it analyzes the input that is given from the given by the sensors, and then it acts accordingly. So how these five organs are important in a human body, the same way sensors are important in IoT. So these five organs are again called as sensory organs, isn't it? These five organs are called sensory organs. So the surprising point is that almost all present day sensors took inspiration from one or the other of uh, these what is so called biological sensors. I could say that these are biological sensors, right? So they have taken inspiration from one or the other of these biological sensors. So let us look at some analogies how the sensors have taken inspiration from these biological sensors. The first analogy is between an eye and a digital camera. So you know the analogy between an eye and a digital camera, isn't it? Because in an eye what happens is that the light that is coming from an object is getting focused by a lens that you have in front of your eye, and it focuses this light onto photosensitive regions of your eye where your rods and cones are located, and there it makes a meaningful signal. The stimulation that the rods and cones got, it will be transferred to the brain for interpretation, right? So biology says that you have almost 120 million rods which are responsible for black and white vision, and 6 million cones for color vision. Exactly the same way, if you look at a digital camera that you are seeing over here. So here I have taken an image without the lens. So what you seeing here is exactly the middle part is called the CCD. So this is exactly similar to your rods and cones. This is the place where the entire sensing happens. And you have a lens that you are attaching on the top of this that focuses the light that is coming from any object that you are zooming in. It effectively makes sure that the light falls in the proper way on this CCD, and then the signal from the CCD gets transmitted to the processing unit of the camera, and then it is converted as an image, right? So you know that all these cameras are coming with a specification of 20 megapixel or 30 megapixel or 34 megapixel or something like that. But you should understand that human eye has 576 megapixel. So this is one of the analogy that we have, or this is one of the inspiration to make a present day sensor, right? Another analogy is between a human ear and a mic and a microphone. So in a mechanism of voice generation and reception, when I am talking from here, the air in my lungs set my vocal cords into vibration, and these vocal cords, the vibration that is generated by the vocal cords will be tuned, fine tuned by my tongues and all those things, and it will be traveling to the air and it reaches my audience ears. So after passing through the auditory canal, it goes and falls on an eardrum, right? There's a membrane over there, and it makes a vibration on the membrane, and this vibration is then carried into your brain for interpretation. So one of the key elements over here is the membrane, the membrane that you have in your ear. Exactly the same way, if you remove this cap of your microphone, you can see a membrane inside that. And when you talk, this membrane vibrates, and this vibration will be sensed by capacitive methods or another suitable method. Um, then it will be transformed into electrical signals and then stored, or it will be reproduced using a speaker. So this is another analogy where an inspiration from a day-to-day life thing or a human thing or a biological thing is getting converted into a physical sensor. Another analogy is that you know that when somebody touches you, you can easily identify that okay, somebody touched you, and more than that, you can understand where he touched you or where he or she touched you, and how hard or how soft was the touch. So your skin, the next sensory organ, is is able to interpret a touch effectively. It is able to localize the touch. It is able to say at what point your touch happened, and it is able to say how hard or how soft was touch. Exactly in the same way, researchers or scientists have developed touch sensors. And one of the classical example of such kind of a touch sensor is the typical touchpad that you see in your laptops. And with that, you can understand, or the machine can understand where did you touch, at what point of the touchpad did you touch. So the XY coordinates are easily, recognized or understood by this mechanism. And you can also control the amount of pressure that you are applying onto this touch sensor, and with that you can convey another set of information onto this computer. So this is another analogy that we have from our day-to-day life. And the other two things that I'm going to discuss right now may not be that common to everybody, but just understand that we have our nose that is capable of detecting the smells, right? So smell, basically the molecules of smell are of different size, and the receptors in your nose are tuned for some sizes. And when those receptors receive those molecules, it will send a signal to your brain saying that okay, this smell you got, and that's or that is that smell, or this is this smell. So scientists have developed exactly the similar mechanism. It's called an electronic nose, where your smell molecules can be identified and can be converted to an electrical signal. So one such example is shown over here, and here you can see that it's sensed and it's said that it is chlorine A. And the last analogy that I have with me is a tongue. And you know that you can you have say 5 tastes, and then a hot and then fat. So in total you can sense 7 different kind of tastes. And for that also people have come up with another option, where you can understand the taste, or you can understand whether a food item is spoiled or food item is made correct. And so such kind of things are possible. So in summary, what I want to say is that almost all sensors that we see in practical applications took inspiration from some of the biological systems. So when we learn about IoT also, we have a lot of correlation with our body, right? So one of those correlation is this that I just mentioned at the beginning part of my lecture, where when you wanted to work forward, your eye will see the way forward. It will say the brain, or it will take images and it will convey to the brain, and then the brain will interpret whether you can go forward or you cannot go forward. Then it gives a signal to the leg, okay, you may go forward or you may not go forward, right? Similar way, in an Internet of Things, you have several connected sensors that are implemented in different environments. For example, when you have a vehicular management system in Internet of Things, you have a set of sensors that are positioned over there that gives you a lot of information. And this information is being interpreted at a central part, where the decision is made, and then the decision is conveyed to another part of the vehicle, or another part of the system, IoT system, to do some part of the work. So in the similar way, when you have an IoT to control the activities that is happening in an industry. So, for example, an IoT that manages the assembly line of a car manufacturing thing. So, the sensors that are employed in this manufacturing line could easily detect whether a task is finished or not. And when it is finished, it will give a signal to the central processing unit for the next action to happen. So, as I said, the analogy between the human things and the Internet of Things, let us go to the depth of our topic today, that is smart sensors. So, here, instead of just going directly into smart sensors, I'll be going through the basics of sensors, what are sensors, and how a sensor system works. And then I will say how a sensor became smart, and finally I will lead to some of the potential applications of smart sensors in IoT. If you have, I wonder if you have ever noticed first generation sensors, if you have ever seen first generation sensors. So most of the first generation sensors were bulky, slow, delicate, and inaccurate. And many of them were purely mechanical in nature. For example, the gyroscope that I have shown in the first example over here is purely mechanical in nature. So the rings that you have over there understand the tilt that is happening to the entire system. And the touchscreen that you are seeing in the middle is a bulky touchscreen that has a lot of electronics going into that. And it is not as accurate as what you see in your present day smartphones or present day tablets or anywhere. It was just an approximate or kind of a crude touchscreen that was developed in the beginning. And in the same way, you have an accelerometer also over here. The first accelerometer, this is a picture of the first accelerometer that was reported. That was also very bulky and inaccurate in nature. So then, as time evolved, several things happened in several modifications happened in all these, and several revolutions happened in all these domains. That finally gave birth to the present day sensors. So, what is the mechanism, or what is the philosophy of the present day sensors? So, when you have a physical phenomena to sense, you have a transduction mechanism to convert these physical phenomena to an electrical signal. So this is the whole philosophy of a present day sensor. Okay, so the transduction mechanism could be very simple, like a change in resistance or a change in capacitance, and it can go all the way to complex transduction mechanisms such as a radioactive decay or a change in the intensity of light, and so on and so forth. So as an example, when I cite a pressure sensor, so this is the most common, or this is the most simple kind of a sensor that I could explain to all of you without much difficulty. So in a pressure sensor, when somebody asks you to make a pressure sensor, the first intuitive thing that goes into your mind is that how can I sense a pressure? And before that, then you ask yourself, what can a pressure do? A pressure can make a deflection, right? A pressure can make a deflection. So now your whole thought process will go in such a way that if I make a setup where I can, I can make this pressure to induce a deflection, that is done. That is the major part of that. So here over here, I aim to make an air pressure sensor, and the air pressure, that air pressure is not a very high pressure in normal cases. Okay, with air you can make higher pressures as well, but it's not like a pressure that you are applying with your hands and all, right? So those pressures are of the pressures that the air pressure that you monitor will be of moderate range. So when you're thinking of implementing this pressure sensor, you will think of making a diaphragm that moves when the pressure impinges on that. So that would be the first direction that you will be thinking at. And so that is not enough. You just making a deflection in the diaphragm is not enough. When a diaphragm deflects because of this incoming pressure, you need to understand this deflection. How can you do that? So a deflection means a strain, right? A deflection means a strain. So now you think, what kind of a mechanism can convert a strain to a meaningful signal? You have several mechanisms for that. The first mechanism that you can think of is a piezoresistive material, right? In a piezoresistive material, according to the strain, its resistance changes. So imagine you make your diaphragm with a piezoresistive material, and then you make the air pressure to fall on that. And when it deflects, its resistance changes, and you give a supply across this diaphragm, and as and when the resistance changes, uh, you could easily sense the incoming pressure. So that is the most simple way, or that's the most simpler way that you can implement a pressure sensor. As opposed to a piezo resistive material, you can use a piezoelectric material also. Because if you're using a piezoelectric material, according to the deflection, a piezoelectric material also will give you uh, a change in, or it will generate a signal for you. But the difference between a piezoelectric material based pressure sensor and a piezo resistive material based pressure sensor is that piezo resistive based pressure sensors can be static pressure sensors, meaning as long as the pressure is falling on that, you will get the constant reading. But a piezoelectric based pressure sensors can be used only for a dynamic pressure sensing, because once it gets deflected, at the moment of deflection, you'll get a signal, and later you will not get any signal. So those are kind of dynamic pressure sensors, and you need to have a very small associated electronics that you have over here to to give the necessary supply or take the necessary supply and do a minimal filtering. So this is how you implement a normal pressure sensor. So let us slowly move forward. I have shown this picture of a gyroscope. This was the first generation gyroscope that people have implemented. It's a mostly mechanical system. And say, for example, if this gyroscope was 20 centimeter in length, it had 20 centimeter length. Imagine nowadays you have in your mobile phone, you have a gyroscope, you have an accelerometer, you have touch screen, and you have all sort of things. So can you imagine incorporating all these kind of bulky things into your mobile phone and carrying it in your pocket? You cannot do that, right? You cannot carry in your bag also. So the revolution that converted these bulky, delicate, or humongous sensors into very tiny, small sensors is called MEMS. That MEMS was a very big revolution in this sensor domain. So, for those of you who don't know what is MEMS, MEMS basically is a manufacturing methodology that uses, IC fabrication techniques to make electromechanical systems or micro electromechanical systems, or sensors or transducers or such kind of things. So the advantage here was the technology for making these MEMS devices were pretty established. All the IC manufacturing techniques were established. Therefore, it was not so difficult for the inventors of the MEMS technology to adapt those techniques and make beautiful, accurate sensors. And that is what you are seeing over here. When you had a gyroscope that was having a dimension of 20 centimeter, with MEMS technology, you could scale it down to 200 micrometers, or lower than that. When I'm saying in numbers, this is like 10 raised 4, a reduction of size of 10 raised 4. That was the revolution. That was the biggest revolution that the sensor industry ever witnessed. And when I say the advantages of MEMS in terms of manufacturing, or in terms of applications, the most important advantage the MEMS gave to the sensor domain is that it shrunk the size of the sensors. It made the sensors portable. It made the sensors handy. Right. So the first advantage that the MEMS offered to sensor domain was the reduction in size, mass, and volume. And when the size, mass, and volume came down, its power consumption also came down. So that is a second advantage, right? So when you have a bulky system, so you think about power consumption, because earlier days when you had incandescent lamps in your home, you used to have a lot of power consumption, and later when LED bulbs came up, this power consumption came down, but you had the same functionality with you. So at the end of the day, what matters to you is that are you getting a proper functionality at the expense of the lowest amount of power? And MEMS helped the sensor industry to achieve that milestone where you spend the minimal of the minimal power, and you achieve all the functionality. And thus we were able to, or thus the scientists or the industrialists were able to integrate these tiny small sensors into several systems, because it doesn't make a difference. It doesn't make a difference. So people were able to integrate these kind of small or miniaturized sensors wherever possible. Wherever possible, they started incorporating. But when they were bigger, you had constraints in incorporating them into systems. And of course, as I said, that how IC manufacturing becomes so cheap. It's just because of the bulk manufacturing. If you were to fabricate one IC or two IC, you have to pay in terms of lakhs of Indian rupees or maybe crores of Indian rupees. But when batch fabrication came up, when you started fabricating millions and millions of chips, your cost per chip came down. So batch fabrication give another advantage to the sensor domain, where when you start manufacturing in bulk quantity, you are able to bring down its cost, and of course the fabrication methodology that you are resorting to is a much established and reliable technology. So you were able to get like vibration resistant and shock resistant MEM sensors. So, when you are speaking about a generic sensor system, what do you have in a sensor system? You must have always wondered how this sensor system works. You know that there is a sensor and something is happening, and you are able to interpret all your things. So, basically, in a sensor system, what you have is a sensor or a transducer sometimes. Transducer is something that changes one form of energy to the other, right? So you have a sensor or a transducer which is calibrated. That is very important. When somebody manufactures a sensor, you should calibrate it. So you have a calibrated sensor or a transducer to which you apply your measurement. When you apply your measurement to the sensor or transducer, it converts this measurement into a measurable signal. And this signal, but the problem with this signal is that this signal may have a lot of noise with that, and this signal may be very feeble. It's like few millivolt, or sometimes in microvolt, or sometimes in nanovolt. The sorry, the external signal can interfere that with that, and it can kill the signal that was generated from that. So therefore you need to have a signal conditioning unit which filters out your unwanted signals, or which filters out your unwanted frequency components, and it amplifies your necessary frequency component or necessary signal. So you need to have a signal conditioning unit after that. And and the signal conditioning unit will have a thresholding mechanism or some other mechanism to understand how much it's sensed, or what quantity it's sensed, or how much, or what is the measure that the sensor made. So the signal conditioning unit will have that kind of an option also, and it then feeds to an indicator or a recorder, or a processor or a controller. So this is a generic sensor system. So we have all good with this, right? It worked fine for us. So why do we want alternate or better systems? The reason being, that from the sensor to the signal conditioner, you have some wires going. The wires that carry information from this sensor to the signal conditioner, right? And I mentioned that your output of your sensor or transducer will be very feeble, so that when a wire carries this information, there are chances that because of the RC delay, or because of the drops, you lose information. You lose a lot of information, and you will encounter a lot of RC delay between the sensing and between the interpretation. So you have a lot of signal propagation delay comes in because of the interconnects, and you have, say, power constraints. When you have your systems yeah, like distantly located, you have your sensor that needs to be powered, you have your signal conditioning unit that needs to be powered, you have your monitor that needs to be powered, you have a lot of power constraints coming into picture. And the system is bulky because all these are implemented as different units. Your system became bulky. Now, to come around all these problems, we wanted to have better systems. And even more than that, we wanted the sensors to be smart. We wanted the sensors to be really smart like us, right? We wanted the sensors to be smart. We wanted the sensors to think by itself, we wanted it to act by itself. And that is the most advisable condition. So in this scenario, the concept of smart sensors came into picture. So now the question is, how are sensors made smart? And before addressing this question, as as a definition for a smart sensor, IEEE 1451.2 defines a smart sensor as something that provides functions beyond those necessary for generating a correct representation of a sensed or controlled quantity. It is something, it has got something more than just sensing. It has to do a lot of things. It has to do a lot of processing within itself. So those kind of sensors are called smart sensors. So then how are these sensors made smart? You know that when you need to do a processing, who can do a processing? A processor can do a processing, right? So when you have a processor, when you are having a processor, a default unit that comes with the processor is the memory, because you are processing some sort of data, and this data has to be stored somewhere. So a smart sensor should have its own associated processor, its own associated memory. And this processor could be a microcontroller, or it could be a digital signal processor, or it could be an IC that is made specific for that application, which is called application specific IC, or ASIC. Or it could be a field programmable gate array. So any of those things can be incorporated with sensor plus memory will give you a smart sensor. And so, when we are defining a smart sensor model, how can we define a smart sensor model? Over here, you can see the sensor element, its signal conditioning and amplification, its analog to digital converter, its controller, its memory. You have all these things attached to one place. That is, at the signal node, you have all these things present to make the sensor smart. And then with a bidirectional bus, or with some other mechanism, you send this to the main control unit, that is the MCU. So when we are talking about the levels of integration in a smart sensor, you can categorize it into 5 levels of integration. In the first level, maybe the first 3 levels, you cannot call it as a smart sensor. You can just call it as a sensor with associated electronics. That's it. So in the level 1, it comes as the discrete signal, like discrete elements, where you have a standalone sensor over there, and from sensor you take out the signal using wires, and then you feed it into the necessary circuitry. So such kind of an implementation is called level 1, or discrete device level implementation. In the second level, you have a very basic integration where the sensor is attached to an analog circuitry. You have a small analog circuitry that goes along the sensor. So this analog circuitry can do very much minimal functions. If you remember our pressure sensor, you had the sensor on the side, and you had a small circuitry over there, right? But these sensor and circuitry were not implemented on the same place. They are located a little apart, right? So you have a sensor with a separate analog circuitry. So the example that I had shown over there can be considered as a level 2 or basic integration of a sensor system. And in the level 3, when you have sensor with integrated analog circuitry, if you are able to integrate analog circuitry with the sensor or on the sensor die itself, okay, so that kind of an integration is called a level 3, or mixing of technologies. And in the level 4, you can say level 4 and level 5 are considered as smart sensors, where in the level 4 you have a CMOS compatible sensor that is integrated with analog and digital circuitry. So what is the meaning of a CMOS compatible sensor? Let us spend a little time on what is understanding what is a CMOS compatible sensor. You know that most of you are from the electronics background, and you know that when you're fabricating an IC in a clean room, your clean room should be extremely clean, right? And you have certain materials that are allowed inside the clean room and certain materials that are not allowed in the clean room. So my first question: why do you need an extra clean environment for the fabrication of ICs? So I'll say the answer myself. You may have answers in your mind, but I'll tell the answer myself, because the size of the transistors that you make in today's circuits, or you have in today's circuits, are in micron size or less, right? You can see that today's processors come with 14 nanometer technology or 10 nanometer technology. So that is a gate length. So you have your transistors coming in some hundreds of nanometers length maximum, and one dust particle in this room can spoil, say, hundreds of transistors, or it can make hundreds of transistors not working. And if at least one transistor goes bad, your entire circuit will not work, right? Your entire circuit will not work. So you have a necessity to have an extra clean environment for the fabrication of these sensors, and at the same time you have restrictions in having certain materials inside the clean room. For example, carbon is a very big contaminant in a clean room, because you must have studied about the interface traps and all those things that are there in a MOSFET. And if you have these kind of elements that is coming inside the fabrication process flow, that will deteriorate the performance of your transistor or the circuit that you're making. So those materials that are allowed inside the clean room are called CMOS compatible materials. So or here, when you are making a sensor that can be integrated with the analog or digital circuitry, you should ensure that you are going to make this sensor with CMOS compatible materials. If you are going to make it with a non-CMOS compatible material, then for sure it is not allowed inside the clean room, and therefore you cannot make your sensor along with your circuitry. So that is one of the trademarks when you go into smart sensors. And the level 5 is the full integration, where you have your CMOS compatible sensor integrated with analog and digital circuitry and the RF circuitry. Meaning you are able to transmit your signal from the sensor node. You made your sensor node self-reliant. That is what is happening in the level 5. And now I will highlight few of the mechanisms by which smart sensors are made. So you know that what is a smart sensor, right? A sensor with its own processing and its own memory. That is the simplest definition of a smart sensor. So how will you integrate the processor and a sensor? So first mechanism by which you can integrate a sensor and a processor is the monolithic integration, where you fabricate your integrated circuit and your sensor on the same chip, on the same wafer. Okay, such kind of an integration is called a monolithic integration. Or monolithic, the word meaning itself is formed on a large block of stone. So basically, it's stone itself, right? The wafer that you're making is a stone. It's nothing but it's silica, it's silicon. So there is nothing wrong in calling it as formed on a large block of stone. It makes sense over there. And you fabricate your circuitry and your sensor at the same place. Not may not be at the same place, but close to each other, but on the same die. Such kind of an integration is called a monolithic integration. And this monolithic integration is
Joseph, I think there is some connection problem with Joseph. Let us wait.
Extremely sorry that my this was disconnected. My internet was disconnected. So let me. So is my screen visible? Can somebody tell that?
Sir, not yet, sir. We cannot see your screen.
Hello?
Okay. Okay. Let me share my screen once again. Okay.
Sir,
So is my screen visible now?
yes, sir, we can see.
Yes.
Okay. So sorry for the interruption. My internet got disconnected. So I think that I was able to convey everything properly till monolithic integration, right? Or my right, my network went bad before that. Okay, I'll once again go through the monolithic integration part and to make sure that everything was properly conveyed. So in the monolithic integration, what you are going to do is that you are making the processor and the sensor in the same chip. So that is called a monolithic integration. The word meaning of monolithic integration itself is that you are forming everything on the large block of stone, and that makes a lot of sense over here because you are making everything on silicon, and silicon you can consider it as sand and stone. So everything goes hand in hand, right? So monolithic integration, the word itself makes a lot of sense where you fabricate your sensor and the associated electronics on the same chip. But when you're going to fabricate such kind of a chip, you have a constraint. The constraint over there is mostly the constraint is with related to the temperature, and especially this is prominent when you have a post CMOS fabrication process, meaning after fabricating your CMOS chip, if you are going to fabricate your sensor, you have to be very careful regarding the temperature that you use in your fabrication. Because if you increase the temperature more than a particular limit, it can lead to the source and drain degeneration, or it can go deep, or it can lead to some metal melting inside the IC, and it can lead to a lot of issues. It can induce thermal stress, and so anything that is post CMOS compatible should be made within a particular temperature range. So if you know that your process needs a high temperature or your fabrication process needs a high temperature process, then you should go for pre-CMOS fabrication process where you should first fabricate your sensor on the chip, and then you go ahead and fabricate the IC. So these are the two types of or these are the two classifications of monolithic integration, that is pre-CMOS and the post-CMOS fabrication process. I have shown an example over here that which I was taken from which was taken from this publication, that you have all these gray areas as the circuitry, and over here you have a sensor integrator, right? You have now within the same chip you have everything incorporated. And advantages are, of course, miniaturization, because as opposed to having sensor and the post processing unit separate, you have everything in the same chip. That made a lot of saving the space. And of course, because of less signal propagation direction, like signal propagation paths and all those things, you have a lower power consumption. And you have an increased operating speed also, because the RC delay will come down, and improved functional performance can also be achieved. But at the same time, you have to be careful about having a sensor at a particular power rating only. You cannot have a sensor with a very high power rating on the top of a CMOS circuitry that can cause uh, potential damages to the IC that you have realized side by side. And another problem that can happen is a pure isolation between the adjacent components, because they are situated very close to each other. And sometimes, even if you have, say, a moderate power supply, there are chances that it could leak into the other units, other circuitry units. And the process constraints and the temperature, which I had mentioned in the previous slide. So another possible mechanism by which you can incorporate your sensors and or integrate your sensors and your processor or memory is the vertical integration. As an example for this is, if you look at olden IITs or olden NITs or olden bigger campus or residential campus colleges, they used to have separate faculty housing, meaning villa type faculty housing for the faculties. But later, when they started establishing new institutes, what they started doing, they started not going for such kind of villas. As opposed to that, they started going for flats for the faculty housing or staff housing. What was the motivation for that? It's because that you are constrained in the available area. Exactly the similar way, when you have constraints in the available area, when you have constraints in the available area, what will you do? The next direction or the next dimension that you think is the z-axis or the vertical axis. So such kind of integrations where different units of a smart sensor is integrated one on the top of other is called a vertical integration. If I'm explaining it in a little more detail, you have your electronic circuitry fabricated in one wafer. You have your sensor fabricated in another wafer. You have your memory fabricated in another wafer, and you attach it one on the top of other, and you connect it something using something what is known as a true silicon via, which is like an interconnect that is passing through the silicon. This is called a through silicon via. And when you are integrating in this fashion, you are able to save the space. That is one advantage. Then you are able to decrease the signal propagation delay even more. So that is a second way that you can implement a smart sensor. A typical example that I can show over here is one of those sensors or one of those ultrasound arrays that was developed in the group that I was working in Stanford, where the group was mostly focused on developing ultrasound imaging devices. Um, so meaning you make ultrasound transducer arrays that help you to image your human body or anything. So when you want to make a three-dimensional image, you need to have a two-dimensional array of ultrasound transducers. But it was kind of impossible to take signal from each and every transducer element, because you have an array of say 1000 by 1000 or say 500 by 500 transducer elements. So you can imagine how complex the system will be. You cannot route that many signal lines on the top of your ultrasound transducer array. In that case, what they have done is that they have made the electronic circuitry in one wafer and the transducer on the other wafer, and then they have integrated one on the top of the other, which is a very good example of what I have mentioned in my previous slide. So this is the transducer array. This top thing is a transducer array. It's called the CMUD. It's called capacitive microemission ultrasonic transducer, which is integrated on the top of a front-end integrated circuit that is shown over here. Um, and the integration was made possible using through silicon wire. And what are the most common vertical integration practices? There are three common vertical integration practices. The first practice is if you are sure that your sensor, your associated electronics, and your memory and everything that you integrate together are occupying the same amount of area. If all of them are occupying the same amount of area, what you can do is you can devote one entire wafer for fabricating your circuitry. Maybe the top gray wafer you fabricate your circuitry, and then the next blue wafer you fabricate your maybe no, maybe you can devote the top one for fabricating the sensors, and the blue one for fabricating the circuitry, and the last one, the third one for say fabricating memory. And what you can do is the fourth one for some other things, okay, some dedicated things. And if all of them are occupying the same chip area, exactly the same chip area, what you can do is that you can just bring all of them together and bond like this, and you provide connections through all these dies. And then what you do is you dice this entire assembly. You dice the entire dice means you cut this bonded stuff, and you will get individual dice like this. So that is one way of vertical integration, which is called a wafer to wafer bonding, where you are bonding all wafers together. But the constraint over here is that you need to have all your bonding things, meaning your sensors, your associated electronics, your memory, everything should have the same area. But imagine that as a hypothetical condition, because in all cases that is not possible. Sometimes the sensor may be big, sometimes your memory may be big, or memory may be small, sometimes your circuit may be small, and you may not be able to integrate in this fashion where you bond wafer on the top of wafer. It is kind of impossible. In those cases, what you do is you dice or you cut one of these wafers. For example, if you have your say two things that are small. I mean to say that your sensor and the top one is a sensor wafer, and the next one is the circuit wafer. So if your sensor wafer and your circuit wafer are having the same dimensions, or those things are of the same dimensions, then you can attach them together in this fashion and dies, and then attach onto the top of the full wafer like this. And after doing this attachment, you can dice in the way that you want. So that is a second possibility, which is called a chip to wafer bonding, where you have your chips getting bonded onto your wafer. The third mechanism is that if none of them are of same dimensions, what you are forced to do is that you have to cut all these things into individual chips, and you have to select individual chips and bond them together using some bonding mechanism, which is called a chip to chip bonding. Hope these things are clear, and I'm moving forward. Another important aspect that you need to have in a smart sensor is that your sensor should be able to generate its own power, it should be able to manage its own power. These are some of the most critical aspects, because always you may not be able to power up your sensor node and make it work, or you may have to provide a battery with that, or there's a lot of headache for them, right? If it manages its own things by itself, it will be more efficient. So you think in this fashion. You think about your body. So if your body had this capability where when you're sleeping, when your central processing system sleeps, your brain sleeps, if your hand is able to write, okay, then you can write your assignments just like that. When you're sleeping, you can write your assignments, right? Or what I mean to say is that when the sensor unit is able to generate its own power, and it's able to think by itself, then you don't need to bother the central processing unit to generate control signals, or give power for that, right? For that, you can either use solar power modules or piezoelectric power modules for accomplishing these tasks. So another aspect is the power awareness, because at all instant of time you don't need to have your individual sensor nodes to be on. So it should be power aware. It should be aware at what point of time it needs to be on, or goes to sleep, you're saving a lot of power over there also. So power aware systems are pretty much important nowadays. And one of the last aspect that one needs to think about is making sensors even more brilliant. So just having a processor with your sensor, or just having a memory unit with your sensor will not do all the works. What you need to have is an artificial intelligence associated with that. So I think tomorrow you have a session on machine learning for IoT. So there, the one who is taking class will be explaining in detail about the machine learning techniques and how they made all these things extremely smart. But in an abstract, when I'm saying, when you have a sensor and a common sensor, a conventional sensor, what you had is that you have the sensor and you have a thresholding mechanism to understand what kind of a signal it sends, and then it is fed into the application. But in a smart sensor system, you have some data processing, and then a smart model comes into picture, and that models can be implemented using machine learning techniques, which will be covered in tomorrow's lecture. And now let us think of few of the potential applications where you can have these smart sensors being implemented. So over here, what I decided is, instead of bringing some of the already implemented things, I thought of we thinking and we implementing and we bringing some ideas, or the ideas may be existing ideas, but that makes a lot of meaning, right? So let us take each and every of these topic, precision agriculture, point of care diagnostic, and all those things, and let us understand how smart sensors can make these kind of IoT systems more effective and more brilliant. The first thing is the precision agriculture. You know what is precision agriculture, right? In agriculture, you always have to give the right amount of nutrients and right amount of water and right amount of light, and managing all these resources, and the stream of agriculture that manages all these resources in the most scientific way is called precision agriculture. So how can you manage this? You need to have sensors to sense everything, right? You need to understand whether your water level in your soil is up to the mark, or it is low, or it is high, and you have to provide the uh, necessary amount of water, right? And the second point is that you should understand whether the pH level of the soil is up to the mark, or the nutrients in the soil is are sufficient or are low, or the lighting in the ambience is okay. So for all these you give sensors. So, in the present day precision agriculture, what people do is that they take inputs from all these sensors. For example, when you have a moisture sensor or when you have a pH sensor, you make these individual sensors to sense the pH or sense the moisture and send those data to a central control unit where they process and understand it is a low water condition or a low pH condition and do the necessary action. If it is a low water condition, it will supply, it will turn on the sprinkler, and then it will put some water. And if it is a low pH condition, it will add some nutrients to improve the pH of the soil, and so on and so forth. So here you had to bother your central processing system to give the necessary inputs to the soil, right? But imagine if you have a smart sensor as opposed to a conventional sensor to sense this physical phenomena. Suppose you have a smart soil moisture sensor. So when it senses soil moisture, it will not just transmit data. What it does is that it will process data in itself. It will analyze and see whether the water level in the soil is enough for that crop, or if it is less, or if it is more. If it is less, what it does is that it can itself give a command to the sprinkler without the help of the central processing unit, right? It itself can give a command to the sprinkler saying that, hey, sprinkler, give me some water. So this avoids a lot of signal propagation and all those things, right? In the similar way, say for example, your light is not sufficient. So all these agriculture are done in controlled environments. So sometimes the light is not sufficient, and then you may have to turn on the lights. In precision agriculture, mostly people tend to give artificial lights and all those stuff. So then you have to turn on more number of lights to give sufficient lighting for those plants. So these kind of things can also be communicated directly to the light instead of going through the central processing system, right? So that is how you can make a precision agriculture more scientific, or more precise, or more efficient with the use of smart sensors. In the same way, in a point of care diagnostic system, uh, can some of you think of such kind of an application of a smart sensor in a point of care diagnostic system? If you guys can unmute your mic and one of you can tell me that, I'll be happy to hear that. Are there any volunteers out there? Okay, so okay, fine. So I'll myself go for that. A point of care diagnostic system. What people aim by that is you have a whole diagnostic setup that is incorporated in some of the gadgets, right? So nowadays, you know that your smart watches are able to tell you some of the physiological parameters. It is able to tell you your heart rate and your it may be able to tell you your oxygen saturation. It may be able to tell your blood pressure. It sometimes, if it can measure glucose content in vitro, if it can do that, it can tell you your glucose content, and if it can give a hint of whether you need an insulin shot, or you're perfectly okay. So such kind of things, where you have all the diagnostics happening at that point itself, is called a point of care system. So, in most of the point of care systems, after taking the inputs, in nowadays, what is happening is that it is being communicated to a doctor, or it is being communicated to an external person, or it's being communicated to a processing environment where the necessary processing is happening and gives an instruction over there. Where it is not like if something is bad or something is wrong, or if your sugar levels are going abnormal, or something like that. And nowadays, you know that you can provide insulin without injection also. You can open your sweat pores and you can give your insulin shot directly without using needles. And now imagine your sensor is able to sense your glucose levels and understand itself that it is not sufficient, or it has got some abnormality where you need some insulin shots. It can instruct its own drug delivery system, the drug delivery system that is attached with this point of care device, to deliver a necessary quantity of insulin onto your body. That makes everything run smoothly, right? So that avoids a lot of delay where you are consulting your external person, you are consulting your doctor, and taking his or her advice, and then going forward. It's always it's always good to avoid the delays, isn't it? And another similar example is a connected autonomous car. In which, now if you go to foreign countries, especially in US, you can see a lot of autonomous cars are coming in the picture. They are doing a lot of testing. Google is doing its own autonomous car, and BMW is doing its own autonomous car, and so many people, even in India also, we started doing Tata Elxsi, I think, started doing such kind of autonomous cars. So autonomous cars, this system also needs, it is also an IoT system, right? It needs a lot of sensors and it needs a lot of processing with that. So when such a car, if it happens to drive, or if it happens to commute in a foreign environment where the traffic laws are kept well and good, it is okay to have the sensor to sense and transmit the information to a central processing system and get its feedback and do some actions. But in this kind of scenario where you don't know when a car will come and hit you, or when an obstacle falls in front of you, so what you need to have is, or what is always better to have, is a smart sensor associated with this connected autonomous cars, where the decision is made instantaneously, then and there, and action is made according to that. So if you wanted the car to brake instantaneously, it can brake at that time, right? So incorporating a smart sensor in an autonomous car or connected cars can bring such kind of revolutions. And the same way, you can take it as a home assignment, where you can think of a smart retail system, uh, as opposed to the current day sensors. It's also an IoT system, right? Smart retail systems or IoT systems. You can take it as a home assignment and think, how can smart sensors improve smart retail systems? And you can think of many more such potential applications where smart sensors can make the IoT systems better and better. But what are the challenges for smart sensors in IoT? Problem is that we know, in the smart sensor you have all these associated electronics and all these uh, memory things and everything associated with the chip, right? Your sensor chip, where robustness is an important factor. You are deploying your sensor in a real-time application where your sensor may be robust, but you should make sure that your circuitry is also robust, or your memory is also robust, right? Otherwise, there is a chance of potential failure where your entire system will break down. If your one node breaks down, there are possibilities are that your entire node can break down. So you should ensure that your smart sensor is robust enough. The second point is that it should be self-sufficient in terms of power. If you want to deploy it in a place, and if you want to forget about that for a long period of time, or if you don't want to go and change its battery, or if you don't want to supply electrical power to that, then you should find methods to bring power self-sufficiency. You should incorporate some mechanism to harvest energy from the atmosphere, or generate its own energy and then do its own activities. Then in hardware requirements also, you have some kind of processor requirements, you have some kind of memory requirements and all those things. You have to make sure that you meet all those hardware requirements for the smart sensors. And in the same way, also, you have some software requirements, because when you have a processor and when you have associated processing over there, um, you have to involve a lot of software with this kind of systems. So you need to develop efficient interactive softwares that can manage the situation very well. So these are the main challenges that you have for incorporating smart sensors in IoT. So that is what I have for today. And if there are some doubts, I'm happy to, answer them. So are there any doubts for this?
Yes, in chat box,
Okay, okay,
some persons put ask some queries.
okay,
First one,
okay, sure, sure.
how is it possible to do precision agriculture on a large scale?
Okay, so Precision agriculture is one of the most important thing that the world is looking at, especially when I'm saying about an example of a country implementing precision agriculture is that. So, can I get a minute? There are a lot of disturbance from the other room. Can I just tell them that it's a little more? I'm coming back. Sorry for the interruption. So when you have, when you look at Israel, Israel is a country where you have very opposing environment. Like it's full of desert, and where you have most unfavorable condition for agriculture to go forward. And what they have come across, or what they have come up with, is precision agriculture over large areas, and they have managed each and every drop of water or each and every unit of fertilizer in the most efficient way by using sensors, and then produce the maximum output out of their agricultural activities. So yeah, of course you can do precision agriculture over large areas. You can do in acres and acres. People are doing that. I think in India, we have a tie-up with Israel, and at the same time, we have our own companies doing this kind of. Especially Mahindra is doing a lot of work in precision agriculture, and yeah, and there are many small companies also doing the same. So of course, it is possible.
Next query is it possible to use in plant disease identification?
Yeah, so virtually, if you are able to identify the pathogens that are causing problems in the plants, if you can develop sensors to do that work, of course, you can detect. You can detect, because see, you don't really understand the potential of sensors. You know the current scenario where you have COVID, and several people are coming up with new ideas to detect COVID virus, right? So in the same way, you can detect pathogens that are causing problems for plant diseases, and then you can. It's possible. It is possible, of course. So next
Okay.
question.
Uh, one participant wrote, we were also
Okay.
expecting types of sensors, classifications of sensors, and their applications with examples in IoT enabled devices, etc.
Okay.
during this session. How the
Okay.
sensors will be connected to any devices, will collect the data, store the data, transfer the data, etc. Kindly cover these points.
Okay, so I can, what is the best possible thing I can do in this case is that I can give a tutorial separately. I mean, I can make a tutorial and share, because today's session I wanted it to be mostly on the uh, part where how the sensor got its smartness. That was my aim to cover today. Um, if such a scenario is there, I did not have the material for today's presentation to cover the type of sensors that we have or its classifications. It more of a textbook material is what I think. It's more of a textbook material. What is more interesting for us to learn is that how the sensors became smart, and so that was my motive of covering today's lecture. Yeah.
Okay, thank you,
So if
sir.
it is
What?
needed, I can provide as a different tutorial or something. Yep.
Okay.
I can do that.
Uh, one query is, sir, will such
Okay.
sensor be low cost?
Always sensors became low cost according to the number of pieces that you make. So I had given an example in the beginning that if you are going to make individual chips or individual ICs, you may not be able to afford them, right? If you are just making one microprocessor or two microprocessors only in one run, your cost may be in several millions of dollars for one processor. And so if you can scale up the production, if you can, for example, when you're doing the MEMS devices, if you wanted to produce in large number, of course you can bring down the cost, and we are bringing down. See, almost all the sensors are very cheap nowadays. You imagine your 3,000 rupees or 4,000 rupees smartphone that has how many sensors in that. And if somebody is able to sell a smartphone for 4,000 rupees, what would be its manufacturing cost after deducting the profits and all those things? So, and imagine how many components are there in a smartphone, and imagine what could be the cost of a single sensor. It would be very, very minimal. You can say in few tens of rupees or maybe few hundreds of rupees, right? So you can, of course, depending on the scale of fabrication, you can bring down the cost. You can do that.
Okay, one more query.
Okay.
That is 1 minute. Is it possible with the sensors
Okay.
we are using in laboratory environment in Indian climates?
I did not get the question properly. So can
Okay,
which was that question?
dear
Can you read it?
participants, uh, the resource person is having the background of um, what do you call the VLSI design of sensors. His area is that.
Yeah, sensor
So
fabrication and all
he
those things.
can
I did not get the
confine
question. So,
your queries can be confined to that. Generally, we'll get the details from reading this survey papers. Okay, so
yeah.
I think we can
So
wind up
in
this
1.5 hour lecture, so I may not be able to
related to
cover
his
all things.
expertise area. If any queries, you can ask. Otherwise, we will wind up the session. I invite Renzi sir to propose vote of thanks.
So I hope you all had a very interesting session about sensors and how sensors are used in IoT. So Joseph has shared about the key concepts using analogies, which we can never forget. So that is one of his specialities. And he has taken in that valuable time to share about the recent advancements, especially about MEMS technology and how they are being used for IoT. So I think it has given a good insight into research areas also, because how ML can, machine learning can be used in sensors. So we are grateful to Joe sir. He's our own alumni for um, uh, giving the valuable time and spending the time with us and sharing his expertise, sensor technology with all the participants of this FDP. So on behalf of LBS College of Engineering and all the participants, we want to thank you, sir. We thank you for joining and being part of this FDP. Thank you, sir.
Thank you. Thank you so much.
I would like to make some
All the
more
best.
announcements. Uh, So hope you have understood the flow of our FDP. Today we are there are different components for Internet of Things, and we are actually looking into each of those components, and we have asked these resource persons to share about the recent trends or recent areas in each of these technologies, like sensors, uh, communication, computing, and so on. So we have that flow. So each of this session, you can hear some fundamentals as well as you can hear about the research areas. So we have shared the schedule with you. There are some minor changes in the schedule, which so we'll be recirculating the schedule today. And tomorrow we have a session on machine learning. So how this sense data, how we can process it, how we can use it. This will be shared by our resource person tomorrow. So we require some, we require you all to get prepared for that. There will be some hands-on session. So we will be giving you the instructions in the WhatsApp. We require tools like Colab and Kaggle. So we will circulate you the links, but please install those software components, get familiarized with them so that you also can do some hands-on tomorrow morning at 10 a.m. And we have asked the resource persons for the PPT, but some of them have expressed their concerns. So if they share, we will be sharing it with you. We will be sharing the feedback link also. Kindly wait. And I also request that all the participants to rename themselves with their name, because we are going to take attendance automatically. So we need your name. So kindly rename yourself with your name. Even now, some of them have not renamed. We can see Galaxy mobile phone name. So kindly rename them so that we can collect your attendance correctly. So thank you for joining today's session. Tomorrow's session will be at 10 a.m. We will be sharing all the feedback links, and whoever is sharing the PPTs will be sharing with you. I hope it is clear for everyone. Thank you for joining us. See you all tomorrow. Bye-bye.
Okay, thank you all. See you tomorrow. If any query is there, you can post it into WhatsApp group also. Okay. Thank you.